Hi everyone, this is Ms. Granucci here, and I'm here to talk about the next part of the lesson of kinematics, with acceleration. Again, with all the mindset of how we model motion, right? So as you can see right here, we have three cars, and if you give it a second, let the animation kind of reset here, you can see that they're moving differently. I think you can just automatically look at that. But what I want you to be able to do is kind of quantify this motion. You know, are there some that are moving constantly? Are there some that are accelerating? Which one's accelerating more, less, etc.? And then you can see on the graph right here, you know, which of these motions model the graph that we have. So in essence today, what I want to do is talk about acceleration, a changing motion. So you should be able to define and describe some acceleration scenarios, calculate acceleration, read acceleration on a distance, velocity, and acceleration graph. Represented with a vector or dot diagram, and be able to calculate values of displacement, velocity, and acceleration depending on the type of motion graph that you have. So a lot today. So here we go. Acceleration is a changing motion, so it could be honestly anything. So what I mean by anything, by the way, let's take that, there we go. What I mean by anything anyway is it could also be slowing down. A lot of times people mistake acceleration as going faster. Although that's partially true, you're changing your speed, you can also slow down for acceleration. It's any sort of change in the value of your motion. So slowing down and speeding up. Now you might say, well, there's deceleration for slowing down. You're right, you can use that, but it still quantifies and qualifies as acceleration. So you can see the changes in magnitude. Now remember, magnitude means value. So anytime you change your value of speed, you have an acceleration. But remember, velocity has a direction piece too. So anytime you change your direction, you accelerate. So, you know, some examples like moving backwards and forwards, that's an acceleration because you change your direction. If you start moving north and then go east, that's a change in direction. You've accelerated. And anytime you go in curves, you're going to accelerate. So I have this little diagram right here of an object that is experiencing curves or circles. And when you change your direction, you change the when you change the direction, you have acceleration. Now we looked at these diagrams earlier, but just to compare, you'll notice that when you have different lengths of space in between the dots, you're going to have acceleration because you're changing the distance interval over time. So that's a good note. Anytime you change your distance interval over time, that's an acceleration. That's also true for these values right here. So all of those velocity lengths are different, which means the value of the speed is changing, which means you have acceleration. So we could model acceleration both mathematically and graphically. So the most basic way to describe acceleration is to change the velocity over time. So as you might imagine, VF stands for final velocity, VI stands for initial velocity over t for time. It's total time, so usually we start from 0, but it's not always the case, so that's why we have it written as a delta t right here. Specifically for AP students, what you have is you won't see this definition on the equation sheet, you see it rearranged. So if I take this t and I bring it up to the other side of the equation, and then add my initial velocity, you have VI plus AT. So these are actually equivalent. So actually, I prefer this one just because it's easier to use. That's my personal opinion, but either of these both calculate acceleration. Now, I have to, of course, tell you that this, once again, is average acceleration. So we pick an initial point and a final point on a velocity versus time graph. And that's essentially, you can see a change, right? A change in velocity over the change in time right here. So once again, just be careful with this. When you have a velocity versus time graph, just like we did an example in class, you'll find that you can have changes in the velocity, but you only get the average of those changes. So it's only when you have constant velocity like this right here, a straight line, then you actually get the one true value of the acceleration. In fact, when your average velocity is equal to, how do I want to say this? It's only when you have constant acceleration that your average velocity equals the velocity at any point. I hope you got that. So let's move on here. Oh, before I do, so notice that we have the acceleration values here. So what that means is that the units is going to be in meters per second because of velocity over seconds. So when you simplify this, you get meters per second squared. So let's take a look at this. This is really interesting. Acceleration describes what's happening to the object's motion. So think about it that way. It doesn't necessarily tell you if you're going faster or slower unless you have more information. So in order to figure out if you're going faster or slower, you need to know what the velocity is doing. You need two pieces, velocity and acceleration, to describe what the object is doing. So with that said, when the velocity vector, the arrow, and the acceleration vector are in the same direction, you'll get an object that speeds up. So if you look at the beginning of this animation, you'll see that the velocity vector and the acceleration vector are the same. When you have that case, you speed up. So the opposite is true. So if you are slowing down, the two arrows will be opposing each other. So the acceleration going different than the motion, that's a slowdown. So that's happening here and here. But then we have a time when we actually curve. An object will curve if the acceleration is pointing inward toward the curve. So look at how this is moving. When it points inward toward the curve, we have when the acceleration is perpendicular to the, I'll say it this way, when the acceleration is perpendicular to the velocity, you get a curve, just like you see here. So anytime you have a perpendicular velocity and acceleration, that object will move in a circle, or curve. So I say curve because it doesn't have to go completely in a circle, but it will curve. So let's take a quick look at this example right here. So let's see how we can use, the equation that we have. So let's open up, let me grab this, hold on one second. It's a live recording, right? So I'm just grabbing my pen here. Where is it? Here it is. Sorry about that. All right, let's go ahead and do this. And then we're going to go ahead and pen Sketchpad. See, I did not draw that. Let's do new. No, garbage. Okay. So let's go ahead and do, where's my sketch pad? Give me 1 second. Alright, so that's not going to work. That's alright, we'll use this. Okay, and what we're going to do, just bear with me, I know this is taking a little more time than I anticipated. There we go. So we got both on the screen right here, right? Okay, so this is a type of acceleration problem. So right now, things are straightforward. So I'm going to go through this with more tedium that you probably need. But I just wanted to let you know that if you start doing problems like this, things will be a lot easier. So, okay, so we have an acceleration problem. So we have a car that slows down from 23 meters per second to rest in 7.39 seconds. So what I'd like to do first is I'd like to write out our variables here. So let's see, a car slows down from this to that. So from indicates that's a final velocity. So V, let me get my brush here. So V final is going to be 23 meters per second, like that. So that's my final velocity because I'm going from that. I'm sorry. Ooh, big mistake. Let's go ahead. My final velocity, my fault. Okay, so we're going from this to this. So my final velocity is rest. which is 0. So the reason why is because we started with an initial velocity of 23 meters per second, like that. And it took us a time of 7.39 seconds, like that. What is the car's acceleration? Units, meaning of the answer. So notice that what I did is I took out information from the problem and assigned them a variable, and I listed it vertically. Because I find when I solve problems and I have the list vertically, it's going to be a lot easier to pick the equation that we need to solve the problem. So I'm going to go ahead and just expand this out so it's nice and big, because we have the bulk of the problem, right? And also diagrams help. So what we have is we have this car here, and it goes over here, and we start off at 23 meters per second. We end here, and it took 7.39 seconds to do that, okay? So I like doing pictures too, because you can get a visual of what's going on. So that's my initial velocity, and this is my final. So acceleration is defined as the final minus the initial over t, just like that. And let's continue this paper down. Just like that. Alright, so what I'm going to do is I'll solve for that. So we have all the information. So acceleration is final velocity, which was 0 meters per second, minus the initial velocity, which is 23 meters per second, over 7.39 seconds, like that. So let me grab my calculator. Hold on, it's over here. So 0 minus 23 divided by 7.39. I get negative 3.11, oops. And the units, if you can see here, is meters per second squared. So sorry about the little crunch here. So acceleration is negative 3.11 meters per second squared. Sorry again, it's kind of weird like that. Okay, so what is the answer of this then? So the answer, going back to our problem here, the answer is right here, negative 3.11 meters per second squared. So if you look at my drawing, we're slowing down. So the negative, so my velocity vector, actually I'll do it in a different color. My velocity is going this way, which is the positive direction. But my acceleration is going against, which is what the negative means. It's going against my motion. And remember, when we have acceleration going against your motion, the object slows down. Just like that. So that's what that means. And in fact, that's what we were getting at when we were talking about the situation over here. Sorry, I had a little glitch right here. Okay, so anyway, so that's what I was explaining over here, was that when you have an acceleration that's pointing opposite the velocity, you have a slowdown. So that's what's happening here, and that's what's happening in the previous problem right here, which I was writing, is that the acceleration is opposite the velocity. So that's what the negative really means. Okay, let me go back to this. And in fact, what we have here is all the different ways an object can move based on acceleration vector and velocity vector. So acceleration is a vector. I'm not sure if I mentioned it, but I mentioned now. So absolutely the direction matters. And in fact, this is what happens when you have the different directional pieces. So when there's no acceleration and you're moving forward, or the positive direction, that's moving forward, and you're going constant because there's no acceleration, there's no change in your motion. And similarly for backwards. But look at this. So anytime you have matching directions, you have speeding up. So if it's positive, positive, speeding up forward. Negative, negative, speeding up backwards. And when they're opposite, you get the slowdowns. So you can see the object's motion, but you can't see acceleration. So it's really hard to visualize because you're not seeing the acceleration pointing left or pointing right. You have to envision that yourself. Alright, so this will conclude part 1 of acceleration. I'll do part 2, explaining the graphical parts.